Great. Yeah, looks good. So our next speaker today is Joaquin Masias from Max Planck Institute for Physics in Munich, and he will be talking about dynamical dark energy in type 0B brain worlds. Joaquin, you have 25 minutes. Please go ahead.
Thanks a lot. Okay, so yeah, this work is based on this recent paper in collaboration with Ivana Vasile and Alessandro Boris. So what is the main motivation? So we know that constructing de Sitter spacetimes in string theory is quite difficult. There's a lot of stability and control issues, namely let's say, most well under control proposal is probably KKLT, and that is still under a lot of scrutiny. However, ADS spacetimes are ubiquitous in string theory. They appear, for example, as the near horizon geometry of PPS brains. And they have also been conjectured to be always unstable. At least they have been shown to be unstable in, non-supersymmetric ADS back have been shown to be unstable, at least in every example known. Then the core idea for a dark bubble is the following. Let's say one has a non-supersymmetric ADS vacuum, decaying into a more stable one, meaning one with less vacuum energy or more negative cosmological constant. At the interface of the two vacua, there will be namely a bubble nucleating and controlling the decay. And one can show that the apparent gravity-induced bubble can have a positive cosmological constant. The thing is that because the effective lower dimensional description, in this case we're interested in 4D, will not be a bona fide EFT coupled to gravity. So most Swampland criteria, most Swampland conjectures do not apply to it, which could explain why it's possible to realize the zeta in this setup and not violate the de Sitter conjecture. So in this
Can I
work, we have
interrupt?
started from a non.
Sorry, can I
Yes, please.
interrupt?
Yes, please.
So you're saying ADS would decay to de Sitter?
No, sorry. ADS vacuum decays into a more stable ADS vacuum, so one with a more negative cosmological constant.
Okay, sorry.
And
I guess
the theory inducing the interface between the two in the bubble mediating the decay of the two will have induced positive cosmological constant, or can have induced positive cosmological constant.
Are you going to say more about that, I'm assuming?
Yes, that's this is just the motivation.
All right. All right, thanks.
Thanks. Okay, so here we have started from a non-supersymmetric string theory where namely all ADS vector will be non-supersymmetric. And we have built up an explicit construction of a dark bubble in which de Sitter is realized. So let's start for a quick refresher on non-supersymmetric string theories. I guess probably everyone here knows there's 5 distinct 10D supersymmetric string theories, which are related by this nice network of dualities. From this, it is possible to construct many non-supersymmetric string theories in 10D, but only 3 of which are non-tachyonic. These are the SO16 cross SO16 heterotic non-supersymmetric string theory that we realized from an orbital from many of the two. Yeah, this has no brane content, but the B field is not projected out, so there's still NS5 branes. Then the USP32, also called the Sugimoto string, arises from a modified type P orientifold with O9 plus planes instead of O9 minus. And this theory has a D1 and D5 branes coupling to the Ramon-Ramon 2 form. And as you can get from the title of the talk and the paper, the one we're most interested in is the U32 or 0'B string, also often called the Zagnotti string, which is just an orientifold of the 0'B string. This theory has also D1 and D5 branes, but additionally has a D3 brane coupled to a Ramon-Ramon 4-form field, which will have a self-dual field strength. Now, already from the dimensionality of the brane, we can guess that D3 brane would be ideal to try and realize D equals 4 braneworlds in which we can try to place our universe. But we would also see that these 3 branes are the only branes in this theory will lead to a scale-separated vacua, so scale separation between 4D and 5-dimensional physics. The exact setup for the dark bubble, at least in the simplest realization, is a spherical shell separated into non-ADS5 vacua, where minus denotes the ADS vacua in the inside of the bubble, and plus denotes the ADS vacua in the outside. So the bubble is a thin shell, a thin spherical shell separating the two. And the Einstein equations induced on the brane So the Einstein equations induced in 4 dimensions are implied by the Gauss-Godat equations up to corrections. Then the Gauss-Godat equations, of course, include contributions from the extrinsic curvature, which means this equation is already has non-local contributions to the 4D physics. Yeah, where we also assume, or we write the metric on the brane in this FLRW form. The effective 4D dynamics are given by a cosmological constant of this form, which can be written as a critical tension minus the actual tension of the brane. Yes, sorry, I forgot to mention, this is the tension of the brane. So this is the tension of this thin spherical shell. Whereas the 4D Newton's constant is found to be much bigger than the 5D Newton's constant. Perhaps it's important to say that this construction relies on the fact that relies on the assumption that the ADS vacuum inside and outside have very close cosmological constant. So here, because this difference in the denominator, G4 will be much larger than the G5, or equivalently, the 5-dimensional Planck mass will be much higher than the 4-dimensional. Also, looking at the equation for λ4, we see that if there is no if the brane has no if the tension of the brane is not close to critical, λ4 will be of the same order as λ5, so there will be no scale separation. In other words, the scale separation requires that the brane is nearly critical, which can be achieved by the brane being critical at 3 level and only becoming subcritical by higher order contributions, which is the setup we will achieve in the 0'B string. Also from the Gauss-Godat equation, we can write down the Friedmann equation. It receives a contribution from the positive curvature on the brane because it's spherical shell. But one can also add radiation and matter. Radiation will come from bulk black holes. So it comes from the difference in the mass of the bulk black holes. While while matter can come from the difference in the tension of string clouds in the inside and the outside ADS spaces. So schematically, the picture is like this. One has the brane nucleates, and it realizes the decay of the lambda plus vacuum dynamically, whereas the inside is the lambda minus vacuum. And of course, if this is a brane, one can have strings ending on this brane and extending outside of it. Then for the exact setup, we need to look at the near horizon geometry of TP branes. Similar to the case of type 2 string theory, the near horizon geometry, when these branes are coupled to a FP+2 form field strength, will be approximately ADS cross S given by the dimensionality of the brane. So ADS P+2 times S8 minus 2. Then given a stack of n of these TP brane sorts in the geometry, and a probe stack, a much smaller probe stack, we can find a 3-level probe potential in this form. Then we find that only for p equals 3, this probe potential, this V0 will be the criticality factor. So when this V0 is equal to 1, it means that the brane is critical. We find that it's generally parametrically bigger than 1 for p equals 1 and 5, whereas it is 1 at 3 level for p equals 3. In other words, only these 3 brane worlds will lead to scale separated vacuum. So we proceed to try to build them on these 3 branes. Sorry?
Sorry, could I just ask one question?
Yes, please.
Is it obvious that ADS5 cross S5 background you're looking at is free of tachyons in this case? Tachyons below the BF bound?
I mean, the theory itself is free of tachyons. I'm not sure I understand.
No, the theory itself is free of tachyons, but the background itself, the gravity solution itself, without supersymmetry, isn't obviously stable, I think.
No, that's right. The ADS5 cross S5, it hasn't been proven to be free of perturbative instabilities, in fact. We have examples from ADS7 built on these heterotic non-supersymmetric strings, but the specific case of ADS5 cross S5 is not be proven to be safe of instability.
Right, thank you.
Okay, thanks. Okay, yeah. So the near horizon geometry of a stack of these branes in the 0'B is approximately ADS5 cross S5. At 3 level, the ADS and SPA radii are the same. They will be controlled by essentially some power of the tooth coupling times the string length. But the corrections have different parametric dependence. This will be sorted, because it's a D3 brane, this will be sorted by the self-verified from flux, subjected to this quantization condition. And we can find the C4 potential threading the work volume according to this. So this just solve the differential equation for C4. But these are obviously related by one being the field strength, the other. Then the Bergwell action is just the sum of dBi and Chern-Simons terms. When plugging in F5 and C4 detects this form, and we can compute the probe potential, where we see that indeed the corrections are only logarithmic. So at 3 level, the criticality is indeed 1. Then again, just a reminder, we parameterize the metric on the brane in this FLRW form with flat space like slices. This can be done by identifying the scale factor with the bubble of the radius of the bubble, and identifying cosmological time in terms of the coordinates in the ADS 5. Then the Hamiltonian will be given just by the Legendre transform of Lagrangian, which can be written in this simple form. We can identify this factor epsilon as GS squared times n, or equivalently tooth coupling times GS, which has to be constrained to be very small. Then, as we can see for the equation of the Lagrangian, in the large U limit, the leading term inside the Lagrangian will vanish. So this one would cancel with the one coming from the kinetic energy. And then, because the U4 outside of the Lagrangian will blow up, we require the inside of the square brackets to vanish. Then this gives a relatively simple differential equation, which implies that the scale factor will have this sort of super exponential dependence. So if epsilon m squared was 0, this would just be the theta, but this is some sort of a super de Sitter function. And here m is just the inverse of r, or of r infinity, which is just a ms string divided by tooth coupling to some power. So we would like to try to realize this in terms of 4D physics to study, for example, cosmological perturbation theory. One can try to parameterize this in terms of some general Lagrangian scalar. One can compute the Friedmann equations after some cancellations. It takes this very simple form. But here one can see that h dot will be strictly negative, and simply pass this to the other side. H dot is strictly negative, but for the scale factor that we find, h dot is strictly positive. So this question has no solution for any sort of scalar description. In fact, one can simply compute the equations of state on both sides. One finds that for the general scalar, the equation of state is always bigger than -1. Whereas for the 0'B bubble, the equation of state is always less than -1. The solution of this is considering what's called phantom scalar, so a scalar
Interrupt
field
real
with
fast.
an,
Sorry. So you're violating the null energy condition.
yes, it's a phantom scalar violates non condition. It's also non-unitary.
Okay. Thanks.
Thank you. Yes, so this can be realized via phantom scalar, so scalar with the wrong sign of the kinetic energy. In fact, this sort of exponential expansion, super de Sitter expansion, it's a cosmological scenario which is well known. It's often dubbed LSBR, meaning a little sibling of big rip. So a big rip is a cosmological scenario in which there's a space-time singularity at finite time. In this variation, the space-time singularity is pushed to infinite time. So we find that we find exact realization of this scenario with the phantom scalar with this quadratic potential. At least in a slower world, we can still do a cosmological perturbation theory. We can write the spectral tilt and the tensor scalar ratio, just keeping track of negative signs that appear. It's essentially the same expression as with the normal scalar fields. But however, we find that the scalar description was valid at all times. So we can instead just plug in the full expression for the slower world parameters to compute the spectral tilt and the tensor scalar ratio. Additionally, this same scenario can also be realized via massive freeforms. So a freeform in 4 dimensions has no degrees of freedom. A massive one has 1 degree of freedom. This is what drives this sort of superaccelerated expansion, given that this the potential for the C3 form has the correct shape. And this has a slightly different spectral tilt. It's three halves here instead of 1. Then we can just plug in the expressions we have for the slow roll parameters. And we see that these expressions are always negative. So one has this sort of comically off prediction for the phenomenology. Yeah, these values will always be blue shifted, whereas the measurement shows that they're red shifted. As a comment, we can see that absolute scale invariance, meaning a spectral tilt equals 1, is recovered for epsilon 0, which is expected because in this limit one would recover pure de Sitter. This limit also corresponds to having no NS and S tadpole. So in particular, it cannot be achieved in this non-supersymmetric, in any non-supersymmetric string theory, no 10D string theory. We also studied consequences not for inflation, but for late time acceleration. The 0'B bubble can be parameterized in this W0 WA CDA model, subjected to the experimental results. So expanding this way leads this general shape. So both W0 and WA have the same shape. They are just related by a square. And given Hubble today, this imposes the bound on GS squared less than the cosmological constant today in Planck units, or equivalent GS less than 10 to the minus 60. Now, requiring a large tooth coupling for the ADS description to be valid, then imposes the bound that the number of branes on the stack have to be bigger than 10 to the 60. After a little bit of work, this leads to this following scales in the model. So the scale of what would be the equivalent of the KK scale for the brane well construction is M. This is less than M string, which is less than M10. This is much smaller than 4-dimensional Planck mass, which is much smaller than a 5-dimensional Planck mass. And M will be of order MEV or lower, while the 10-dimensional Planck mass is order TeV. So in principle, this is quite reminiscent of the dark dimension scenario, except that the string coupling is too small to try to realize a standard model gauge couplings in the brane. Being 10 to the minus 6 is probably impossible to try to realize the standard model gauge group on the brane. We can see the result. We can just plot the result for WA and WQ here. We see that epsilon m squared equals 0 is much favored compared to 20 bigger values. And we can argue that this in fact favors models with constant equation of state. See, for example, this recent paper, for a couple of years ago by the group in Uppsala, they break supersymmetry via rotating brane. So they start, I think, type 2 string theory, and they break supersymmetry via rotating brane, and this leads to a constant equation of state, or at least not to a super de Sitter sort of scenario. Finally, we try to study this parametric dependence on epsilon. So epsilon going like GS squared times n is a generic situation. So we look at a slightly different toy model. We consider realizing the bubble on D5 branes wrapping a sum-2 cycle. So we have to assume that the S5 can be replaced by some suitable Einstein manifold with non-trivial 2 homology. And the effective action will take this form over.
I'm sorry, can I interrupt you? Can I interrupt
yes,
you again?
please.
Can you go back
Yes,
to
please.
the slide with the parameters? The WA, W.
Here?
So there's, I guess, 2 parameters that you're trying to explain, and then you're introducing how many more to explain it. I'm not trying to be difficult. Do you have a motivation for why you would want to introduce more parameters to explain 2?
I'm generally not introducing more parameters. I'm not sure I understand the question.
So you've got MS, M10, M Planck, TV, the tuning of N, GS is 10 to the minus 61, and what you're looking at is W0 and WA. what's the advantages of the approach? And again, I'm not trying to be difficult. I just want to see what you'd have to say about it.
So GS is fixed by trying to fit these experimental results on on the equation of state. So requiring that H0 is indeed the Hubble today is what fixes GS to be this small. And then this gives this sort of hierarchy for the scale.
Okay, thank you.
Okay, no problem. No, thanks for the questions, really. Okay, I think I'm okay on time. Might have been a bit fast, actually. Okay, so just to repeat, we would like to study if the parametric dependence on this epsilon can be modified by slightly changing the model. So we try to consider realizing the bubble on these 5 branes, where the extra 2 directions are wrapping a 2 cycle. Yeah, and to this we try to we assume that the S5 can be trace replaced by some suitable manifold that has non-trivial homology. The action is now again the sum of DPI plus the Chern-Simons term, where now we have a coupling between the C4. So to have the correct dimensionality, we have a coupling between the C4 form and the gauge field on the brane. And we have to assume that there's induced C4 charge in the brane according to this equation, so that they cancel exactly, so that the leading order contributions cancel exactly like before. Then we can repeat the same exercise as before. We look at energy conservation at large ADS radius, and this implies the same sort of LSPR cosmological solution with the same sort of scaling for epsilon. So despite all the caveats that one could raise about this specific Thor model, even if one could avoid that, it would still make it extremely unlikely to be able to realize a normal gauge fields in the 0'B string for this sort of for the 0'B bubble, sorry, 0'B bubble. Okay, so to conclude, we have studied a novel realization of a sort of dark bubble scenario in 0'B non-supersymmetric strings. We have seen that it leads to this sort of big rip cosmological accelerated expansion, in which the singularity is not a finite time, but it's pushed to infinite time. We argue why this is unsuitable, completely unsuitable to realize early universe expansion. Instead, we argue that it could, in principle, fit late time accelerated expansion within experimental measures. But the fact that the string coupling predicted is so small makes it unlikely that it can simultaneously satisfy this and realize standard model couplings in the brane, standard model gauge couplings in the brane. Also, I didn't really have time to include this, or I wouldn't have time to go through this talk. But one can show, it has been shown before, that in the presence of a B field, one can realize U1 gauge couplings in the bubble, not the exact value of the coupling, but one can realize U1 fields on the bubble, and they would couple correctly to the induced gravity, which is highly non-trivial. And we also proved that in the absence of a B field, for example, in the 0'B string, there's no B field. This job can instead be done by the C2 Ramon form field. So as an outlook, we have essentially falsified this 0'B construction, but we would still like to look at general dark bubble models. So in general, there are some problems that still remain. So in principle, gravity in the bubble is not a bona fide for the phi, as I mentioned. The equations of motion, the Einstein equations appear from the non-localized degrees of freedom. And the phenomenological implications of these are not, they are still a matter of study. One could try, so if one has non-localized matter, as long as non-localized gravity, the coupling of gravity to matter would look, as we expect, like 2 distant masses would go like 1/r². But if this realized by non-localized strings, these extended strings would most likely be too heavy to realize like light particles. Whereas if matter is not localized, there is in principle no reason why it would couple canonically to gravity, for the gravity. Finally, as I mentioned, U1 gauge fields can be realized on the bubble, and one can show that they couple correctly to gravity. But non-abelian gauge theories most likely do not. And then, given that the low energy sector for universe is either broken, meaning isospin, or confined, meaning color, it is not clear how strong the effect of having non-standard couplings from gravity to non-abelian gauge fields would be. Yeah, I think that's the end of my talk. Thank you.
All right. Thank you, Joaquin, for the very, very, very nice talk. Are there any questions? Vincent, please.
Yes, thanks for the talk. I was wondering, so you said that GS is small and that does not give well, the right size of gauge couplings of the standard model, but I was wondering what the precise relation in this model is between GS and the standard model gauge coupling. Is it just proportional by an order what factor?
I'm not sure. I think one should need to try to realize one should try to break the gauge group on the brain stack. So in principle, without doing anything, the gauge group on the brain stack would be like SUN, right? One should
But I
then try
mean,
to
just
break
of
this
the
further
U1,
to.
just of the
Sorry?
U1.
For the
Like,
U1, yeah, I think it should be, yeah, it should be just 1 over GS, right? Or sorry, square root of,
okay.
is it the square root? No, it's 1 over GS squared, right? The gauge coupling in the
Yeah,
brain.
well, in other dark bubble models, there is a difference of a factor 3/2. Yeah, 3/2. So I was wondering whether
Right.
it's similar. Yeah, but if it's similar, yeah, then I agree. Okay,
Yeah,
thanks.
I think it's similar. No problem.
Thanks.
Any other questions? So, Joaquin, I would like also to ask you. Oh, you can hear me. Yes. Can you hear me?
Yeah.
Okay. So you have like a fandom model, and your Hubble scale, your Hubble factor is not constant, like in quasi-de Sitter cases. How do we know that slow roll approximation is a valid approximation in this scenario? I don't know.
Yes. So, in fact, epsilon tends to 1, to -1, to epsilon tends to 1. Yeah, epsilon tends to -1, actually, in this model.
Okay.
So the slow roll approximation actually gets better with time.
Sorry, I didn't hear you.
The slow roll approximation becomes better with time, one could say.
It
It's
becomes
because
better with time.
because H0 actually tends to 0 at infinity. No, H0 tends to 0 at infinity. No, sorry.
So
H
epsilon
dot over
becomes
H. Epsilon becomes -1 at
small.
infinity. No, epsilon becomes -1 at infinity. So in a sense, it approaches pure de Sitter at infinity. It approaches
Okay.
pure de Sitter with infinite Hubble radius, let's say.
Okay.
Sorry,
Okay,
infinite zero Hubble radius.
Okay, I see. And so where do you measure your spectral index?
Do you mean where? Sorry, what was the question?
I mean, where do you measure your spectral index? Because you have to compare the spectral index with the observations.
Yeah,
So
so it's actually, it would actually not be, if this work would actually not be clear. What would happen after the nucleation of the bubble? It would be unclear if the nucleation of the bubble would lead to something like reheating, or, but in principle, we're just claiming that it would be present in the CMB.
okay, you have a plot, right? Can you go to the next slide just to see the spectral index? Okay, here the NS. Okay, so it's blue shift. I see.
Yeah, it's extremely blue shifted. It doesn't really fit experimental results at all.
And this green point corresponds to infinity, what you said before?
It corresponds to essentially GS squared n equals 0, let's say.
But in terms of time, it's like you take the time to
No,
infinity or what?
sorry, this not time evolution. This is So one looks at the model and one simply changes epsilon m squared. What increases epsilon m squared?
Okay.
These are
Okay.
these are a plot of the parameters only.
All right. We can discuss that later in the discussion. Yeah. Okay. Are there any other questions? If not, let's thank Joaquin for the very nice talk.